welcome back. We are scoring lessons 76 and 77. So I have questions written down and I'll try to get them as we go. Lesson 76, number 1. The woman turns her back to a circular fountain with a radius of 3, randomly tosses a penny over her shoulder into the fountain. What is the probability that her penny lands on the triangular piece of art in the fountain? So again, in general terms, the probability of something, the chance of something happening is what is your desired outcome, that's on top, and what is the total possible outcome. Well, the desired outcome is landing in that triangular shape, and the possible outcome we're saying is anywhere in that fountain. Now, it's sort of a trick question in my opinion because there is also a chance that she could miss the fountain altogether, and that's not accounted for. So we're just going to assume that she is going to hit the fountain somewhere inside the fountain. So what's the chances it's going to land in that triangle shape? And it says randomly tosses it, so we're just going to assume it's all random. She's not actually aiming for that. It's just equally likely to occur anywhere in that round circle. What are the chances it's occurring in that triangle? Your two things are to find the area of the triangle and find the area of the fountain, the total circle. So the area of the triangle is 1/2 base times height. Find that, and that goes on top. That number goes on top, and the bottom number down here is the total area of the circle, which has a radius of 3. If you find those properly, you will get approximately chances of 1 in 100, or about 1%. So again, it's find the area of the fountain, and that drawing is really not to scale because the radius of the fountain is 3 meters, and it almost looks like the radius is 1, kind of that tall leg of the triangle. So it's really not to scale. You have a circle, you have a radius of 3, and then somewhere in there is a triangle, and it's got a radius of 1 here, and then 0.6 here. So it's pretty small. It'd be even smaller than that. So 0.6 and 1 over here. So you need to find the area of this triangle right here, and put that on top, that number on top, and then the area of the whole circle, which is pi times radius squared. So area of the small triangle on top, which is to say this number divided by the area of the circle. So the area of the triangle divided by the area of the circle will get you that chances. Again, it's 1 in 100, basically 1 in 100 or 1%. Number 2, that's really a chart. We really did that one. But completed, can you make a conjecture about rotational symmetry based on the information you recorded? So this is the order of rotational symmetry. Again, I think Suzanne had a question about this. The order of rotational symmetry, and so degrees of rotational symmetry and order of rotational symmetry. What it's asking is if I have a square and I begin rotating it, whether you go this way or this way, doesn't matter, but I just start rotating it. What is the first time, how many degrees till it coincides with itself? In other words, you leave a copy of the original there, and then you get a second copy and begin to turn it. And when will it coincide with itself? When will it be right on top of itself? Well, for a square, a perfect square, with these being congruent, and these 90, when you turn it 90 degrees, it will fit exactly on top of itself. So it has an order, a rotational order of, how is that called? Rotational. The order is, the rotational symmetry, the degrees is 90. 90 degrees of rotational symmetry. That means every 90 degrees it will coincide with itself. And the order is how many times does it do that until it gets back to 360. And it's obvious based on this angle degrees. So something that has 90 degree rotational symmetry means it will do it 9 times. 4 times. It will do 4 times until it gets back to 0. That's including the last one. So a square has 90 degree rotational symmetry, and the order is 4. And for this question, it's asking, back to question 2, it's asking what is the order of rotational symmetry for a quadrilateral, for a pentagon, and these are for regular. Does it say regular? It doesn't, but it should. It should say regular polygons. Pentagon is 5, hexagon 6. It's just how many sides there are, really. If it's a regular polygon, however many sides there are, that many times it's going to lock back into itself. It's going to click on itself. That is, again, assuming you leave a copy there, and you take a second copy right on top of itself and begin to turn it and see how many times it coincides. So 3, 4, 5, 6, 7, 8, 9, 10. 10 for a decagon. That's the answer for number 2. Number 5, graph the equation x squared plus y squared equals 36. This, you should recognize this as a equation for a circle, and that is a circle centered at the origin. The equation, the general equation is x squared plus y squared equals radius squared. And hopefully you can again remember the connection between this and the Pythagorean theorem. Now it's saying graph that equation, but it's using 36. So since it's not 36 squared, you need to find the square root of 36, which means x squared plus y squared is going to equal 6. That means the radius is 6 because 6 squared equals 36, which is what the equation said. So the radius is 6, and it's centered on the origin. So you simply graph that, make a dot here at the middle, go out 6, 1, 2, 3, 4, 5, 6, and 6 this way, get a compass or a string or whatever, and make a circle. It should have a radius of 6. My circle looks bad, but as long as you have a radius of 6, centered at the origin. It'll look more like that. That is number, whatever number it is. Totally lost my place. There it is, 5. All right, number 9. Akila identified this symbol as having 180-degree rotational symmetry. Explain her error. So we're assuming that you made an error. We have to explain it. She says you could turn that shape, make a copy of it, and begin to rotate it 180 degrees, and it would coincide with itself. Well, it would, except for the coloring. It would if it just was a black and white drawing, or no shading, if it was just lines. Then this little teardrop shape would coincide with itself when you turn it 180 degrees. But with one shade being blue, one side being blue and one side being white, if you rotate it 180 degrees, then the blue is going to be on the left and the white will be on the right, which means it does not have rotational symmetry of 180 degrees. So that's the error. The error is, since there's a blue and a white shading, it does not. Number 17. I have to make sure I'm doing this right because there's no one here to correct me. We were at 9, and now we're at 17. Check by calculation that the points P, Q lie on circle C with a center of 1 and 1 and radius of 5. So how do you do this? The way you do it is use the formula, the equation of a circle, and this time you need to use the one that is not centered. It's not the simple one. It's a more complicated one, and the letters are H and K, so x minus H squared plus y minus k squared equals whatever it equals. And we said it has a radius of 5, so 5 squared is 25, so it needs to equal 25 for this case to be true. And then you're going to put in the points 6 and 1. P is 6 and 1, and Q was 4 and 5. Q is 4 and 5, and also the center of the circle is at 1 and 1. Center of the circle is at 1 and 1. So use these points in here and verify that that they all equal 25. So the way you do it is get your x. The x and the y are these. So we're going to try it for this point. So you would say, I should do it right here, but anyways, substitute. This is 6, so 6 minus 1 squared plus 1 minus 1 squared. Does that equal 25? This is how we're checking. So I'm just checking it first for point P, which means this is my x, this is my y, and for both of them, the h and k are 1 and 1. H and k are where is the center of the circle. Usually h is for the x and the k is for the y of the circle, the center of the circle, but it really doesn't matter. You just use these for the h and k, and then you use one at a time, the 6 and the 1, 6 and 1, and then the next time you use a 4 and 5. So in this case, we can see already it's going to work. 6 minus 1 is 5, so 5 squared is 25, plus 1 minus 1 is 0, 0 squared is 0, so 5 squared, 25 equals 25. So we verified that it's true for point P, and then do the same thing for point Q. You're taking 4 for the x, and you're subtracting the 1 off, and you're taking 5 for the y, and subtracting the 1 off. And 4 minus 1 is 3, and 5 minus 1 is 4. Is that right? Yes, it is, because 3, 4, 5. So 3 squared is 9, 4 squared is 16. 16 plus 9 equals 25, so 25 So it works for Q and it works for P. That's what they're asking to do. 21. Tell whether each flag has rotational symmetry. If yes, determine the angle of rotation and the order. So the first flag, the beach, the palm tree there. Does it have rotational symmetry? Well, if it was just an outline of a rectangle, then yes it would, but since it has a picture in there, if you turn it, you have a rectangle, you turn it this way, it's up and down, that's not going to work. You turn it the other way, yes, it's oriented this way, but now the tree is upside down. So no. For the first one, no. The second one, I would almost say no because of the shading of the color. But they say yes, so don't take into account the top left corner of that flag being lighter color. At least in my book, the top left corner and that top left little dot is much lighter than the others. But assume that's not there. If you assume that it's all universal or uniform color, then yes, it has rotational symmetry. And what is the order? As you rotate that 90 degrees, it will lock onto itself again. So the order is 90. The angle of rotation is 90. The order is 4. I keep saying those backwards, but the angle is when does it coincide with itself, and then the order is how many times. So for number 2, for the middle one, you would say yes, it does. The angle of rotation is 90, and the order is 4. And the last one, I would like to say yes, but I cannot say yes because the triangle by itself does, and this star by itself does. But since they're locked together into a picture, and you begin to rotate it, if you rotate it the 60 degrees for this 60 degrees for this triangle, and then the pentagon itself, which is what, 72? It's actually 120. That's what I was trying to. 120 degrees for the triangle. It would take 120 degrees to get over, because it happens 3 times, and the star happens at 72 degrees, which is 5 times, and 3 times and 5 times they don't coincide with each other ever. So as you rotate it around, the triangle and the star together would never match up perfectly. So no, the next one does not. All right. Are we still in 76? Wow. 76, 24. Explain why the tangent of 90 is undefined. Is that we did with that one? No, we did that one. 24. Which is the equation of a circle with a center of -3 and 4 and a radius of 6? Well, the 3 and the 4 are I erased it, but the 3 and the 4 are going to be the h and the k, and the radius is 6. That means radius squared, so the end number should be 36. So it's definitely not a. And then you need to get your 3 and 4, and it's minus k and minus h. So is h first? I always forget. H is first, and h is negative, so that means it's minus a negative number is going to be a positive. It gets confusing, but it is letter B. X plus 3 squared plus y minus 4. And the reason is if you look at the original equation is x minus h and y minus k. Well, since h is -3, then you have to say x minus -3. And x minus -3 is the same as x plus 3. So letter B is correct for 24. 29. Could opposite vectors also be defined as vectors with the same direction but opposite magnitude? And the answer is no. And so you say why? Because magnitude is a direction. It's an absolute value, not a direction. It's a measurement. Magnitude, how long is this? It's 7. You can't have something be -7 long. So the answer is no, and the reason is that magnitude is an absolute value, or you can't have negative magnitude. So opposite vectors are, the correct definition of opposite vectors are vectors that have the same magnitude but have opposite direction. In other words, if it's going this way, +3 and +2, then this way, -3, -2, the opposite direction. Same magnitude, opposite direction. So hope that answers 29. And 30. Reflect square KMRW across the line y equals x plus 2, and they give that line there. So you're just going to, it is a 45-degree angle, so you just count across and go down. So the new, let's start with W. W prime, it's going to be the one closest to the line. W prime should be 6 and 6. R prime should be 9 and 6. M prime is 9 and 3. And K prime is 6 and 3. I'll say them again. W prime is 6 and 6, R prime is 9 and 6, M prime is 9 and 3, and K prime is 6 and 3. Whenever you're reflecting and doing these transformations in a graph like that, it helps to, when you do the original, do the new image, do the prime markers, and also write the coordinates beside them. So that's a quick and easy way for us to score them. Since we're not in the same room, I can't just look at your graph. All right, we're going on, lesson 77. Number 1. Calculate the lateral surface area of a cone with a radius of 3, slant height of 5. The answer is 47.1. I'm assuming approximately there. Centimeters squared. 47.1 square centimeters for number 1. Number 2, which inequality gives the range of the cosine function? If you look back, we did this a couple times, but if you look back on investigation 7, you would have a chart in your homework, you would anyway, and maybe that's the problem, is that we throw our homework away after we're done with it. But cosine goes from 1 to 0, and it includes 1 for a sine of 0. For a cosine of an angle of 0, it's 1, and the cosine of an angle of 90 is 0. So that would tell me it is C, which says y. In other words, the cosine is equal to or greater than 0 and equal to or greater than 1. So the limits are 0 and 1. It includes 0 and goes up and includes 1. So the answer for number 2 is letter C. Number 7, draw 3 internally tangent circles that are tangent to each other at exactly 1 point. I think there's only one way to do this. Different sized circles, they all are touching at one spot. And that one is, but it would look something like that. You could, of course, have them touching on the sides this way, it doesn't matter, but 3 circles, and they're different sizes, and they're all touching at 1 point. And number 11. Calculate the surface area of a cone with a radius of 7, slant height of 10. Round your answer to the nearest square inch. If you use this surface area formulas in lesson 77, just across the page, you should get 374 square inches. That is rounded to the nearest square inch. Number 13, does quadrilateral HJKL with the given vertices have line symmetry or rotational symmetry? In other words, either one, does it have one or the other, and if so, which one does it have? If you graph that, you would say yes, it has line symmetry. It's going to look like that a little bit, not quite that extreme. And so the line is right through the middle. That's the line of symmetry. It's exactly the same amount out here as here and here and here. So yes, it has line symmetry. It does not have rotational symmetry. If you think about rotating this, would not work that way, would not work this way, would not work the other way. So does not have rotational symmetry. Number 14. Which congruence theorem applies to these triangles? The correct definition, or the correct answer, is the HL congruence theorem. It is, those are right triangles that are given as that, and so you need the hypotenuse leg congruence theorem. Some of you may have said side-side angle, but that is not correct. Technically, we don't have a side-side angle congruence theorem, and these are right triangles, so you use the HL, the LA, and HA, and that kind of thing, and you're needing the HL, hypotenuse and leg congruence theorem. Number 18, a waffle cone has a diameter 7, height of 14. What area of waffle dough is needed to make the cone to the nearest square centimeter? 159 square centimeters is the correct answer. 22, describe the lines of symmetry and the rotational symmetry of a parallelogram. A parallelogram, we think of something like this, and it's asking to describe the lines of symmetry. Well, first of all, does it have lines of symmetry? If I go this way and put it across, no, then it should look like this. That doesn't work. If I go this way and do it, it still doesn't, because they're angled like this. So it actually does not have any lines of symmetry. Does it have rotational symmetry? So describe the lines of symmetry of a parallelogram. The lines of symmetry of a parallelogram are non-existent. That's the description. What about the rotational symmetry? Does it have rotational symmetry? Yes, it does. If you go this way, it doesn't work, but if you go this way, it does. So rotational symmetry, and if you describe it, you say it has rotational symmetry of 180 degrees. 180 degrees rotational symmetry is the answer for number 22. 25. Name the type of triangle that has exactly one line of symmetry, and that is an isosceles triangle. Just any old triangle like this, it does not have lines of symmetry. An equilateral triangle has lines of symmetry, but it has more than one. It's there and there and there. It's got 3 or 6, however you count them. So you need an isosceles triangle, which is like this. Exactly one line of symmetry. Isosceles triangle is correct for 25. And the last one, 27. Calculate the volume of a cone with a 1 meter radius, height of 2. Round your answer to the nearest tenth of a meter, 2.1 cubic meters. This is volume, so you should have cubic, 2.1 cubic meters. If that doesn't make sense, go back to the volume formula, 1/3 of base times height, 2.1. All right, we're done.